Okay guys, welcome back to another video. Today we are going to use mathematical induction to prove propositions Pn to be true for all n. And here the step of using the mathematical induction, there will be two steps that you have to do. The first step is the base step, is to show that P1 is true. So try to look at when n is 1 and show that the statement Pn is true. And then once you have the first step or the basic step, the second step is inductive step, is to show that if Pk is true, then Pk plus 1 is true for all positive integer k. So we have to assume that Pk is true and find a way to show that Pk plus 1 is true. Once you can show that, once we can prove this step, we can conclude that by mathematical induction. By mathematical induction, Pn is true for all positive integer n. Okay. So now we will use this theorem to prove a statement or a proposition for a positive integer n. Okay, so we can use this theorem by using this step to prove it. So let's go to the proof right here. Okay, here, this is one of the example of how to use a mathematical induction. Prove that 1 plus 2 plus 3 all the way to n is n times n plus 1 over 2 is true for all positive integer n. Okay, let's prove this. Okay, so we let Pn be a statement or equation containing n, which is 1 plus 2 plus 3 all the way to n equal n times n plus 1 over 2. Okay, this is the well-known formula for many math students. This is the sum of consecutive number from 1 to 3 all the way to n, which is n times n plus 1 over 2. And then we will prove that Pn is true for every positive integer n. So we start with the first step, which is base step. Okay, base step. What is base step? So let n to be 1, okay? And we know that 1 equal to 1 over 2 times what? Times 2, right? Which is what? 1 times 1 plus 1 over 2, okay? It's like we plug in n into 1 and we can show that 1 equal to 1 times 1 plus 1 over 2. So we have the basic step, so hence the base step P1 is true. Now let's go to the inductive step. Take a look at inductive step. What do we have here? So we have to assume that Pk is true. Okay? Assume that Pk is true and try to show that Pk plus 1 is true. Okay, for all, you can say for all positive integer k. Okay. All right. What can we do? So once we assume that pk is true, so we will have 1 plus 2 plus 3 all the way to k equal to k times k plus 1 over 2. Okay. Then what do we have? Then we have to add this number 1 plus 2 plus 3 all the way to k and plus k plus 1. So what happened to the left to the right side? It becomes k times k plus 1 over 2, right? This is the sum of the first. This is the sum of 1, 2, 3 all the way to k, which is k times k plus 1 over 2 and plus k plus 1. And then it turns out to be k times k plus 1 plus 2 times k plus 1 over 2. Okay? And we can factorize k plus 1. So what do we have? We're going to have k plus 1 times k plus 2 over 2. Okay? And then we're going to have k plus 1 times k plus 1 plus 1 over 2, right? Because 2 becomes 1 plus 1. So now we have k plus 1 times k plus 1 and plus 1 over 2, which is the sum of consecutive number from 1, 2, 3 all the way to k plus 1. This shows that from this right here, from k becomes k plus 1. This shows that inductive step is true. Okay, so pk plus 1 is true. Okay, so once pk plus 1 is true, therefore this equation 1 plus 2 plus 3 plus all the way to n times n plus 1 over 2, this equation is true for every positive integer n. Okay, so that's what we have right here in this example. Now let's go to another example. Take a look at this proof right here. So the sum of odd number from 1 all the way to maybe the n odd number, which is n squared. So this we will show that this equation is true for every positive integer n. Okay, we will use mathematical induction. So we start with this. So we let Pn be or denote. Okay, denote 1 plus 3 plus 5 plus all the way to 2n minus 1 equal n squared. Okay, and we will prove that P of n is true for every positive integer n. Okay, and then take a look at this first step. Okay, the first step or the basic step or the base step. Okay, base step. For the base step, we have to show that P1 is true. As we can see, just one is just 1 square, which is pretty obvious, okay? So hence, P of 1 is true. So we have the base step. Now what about the inductive step? Okay. For inductive step, we have to assume that P of K is true. Okay, and try to show that pk plus 1 is true. Okay, pk plus 1 is true. Okay, for any positive integer k. All right, so what can we do with this? Okay, once pk is true, so we gotta have 1 plus 3 plus 5 plus all the way to 2k minus 1 equal k squared. Okay, but we need to have pk plus 1, which is true. Okay, so we also have 1 plus 3 plus 5 plus all the way to 2k plus 2k minus 1, and plus the next one is k plus 1 minus 1. Okay, so what happened to this? So we will continue to do it. So we're gonna have the first one turns out to be k squared, right? K squared plus 2k plus 2 minus 1. We distribute this number 2 into here. Then it turns out to be k squared plus 2k plus 1. And it turns out to be k plus 1 squared. Okay? It turns out to be k plus 1 squared. Once we have this one right here, which is pk, so we have pk plus 1, which is true. So we have shown that pk plus 1 is true. Okay? So therefore, pk plus 1 is true. Okay? Hence, what did we show? We have shown that 1 plus 3 plus 5 all the way to 2n minus 1 is going to be n squared, and it is true for every positive integer n. Okay? Alright, so this is how to use the mathematical induction, especially the first one, the first mathematical induction, to prove these examples. In the next video, we will go to the extended principle of mathematical induction, which is the adaptation of the first mathematical induction. Okay? So, that's it for today.